trivial that I still find quite interesting. The higher order function map can be used in place of a for each anytime you use a for each. In other words, wherever you are using the for each construct in your code, you can always use the higher order function map instead. Further, I would argue that you not only just can, but you actually should at all times. In other words, you can always use the map construct in place of the for each construct, and I argue that you always should. The reason from my perspective being readability, clarity, it makes it easier to understand what's going on semantically. It makes it easier to read the code. It makes it easier to understand what's actually happening. Why? Well, because you have to read the boilerplate. You can focus on the function that's mapped over the inputs rather than having to read all of the for each stuff. Also, you reduce the number of temporary variables. So eventually you could reduce mutation. And mutation usually is associated with complexity in terms of understanding what's going on in your code. You have mutation, you can't always be sure about what value will be contained in a particular variable. This will be easier if you reduce mutation. Now, inevitably, when I say that higher order functions such as map generally are more understandable, are more readable than their sort of procedural counterparts such as for each or for loops or while loops, etc. Inevitably, I think a statement like that will be met by naysayers who argue that it's in fact not at all more understandable. People are more familiar with the for each construct and more familiar with the classic procedural style programming rather than the higher order functional style of programming. So readability should be higher in the for each style, the procedural style. A great argument towards this is something I heard in a video. I can't remember who said this, but I'll link the video in the description because I think it's an excellent quote. Familiarity should not be confused with readability. Familiarity should not be confused with understandability. In other words, that something is familiar should not be taken to mean that it is readable, and vice versa. And in other words, when you get over that initial hurdle of familiarity, you will find that the higher order functions are in many scenarios actually more readable. They're more concise. They are more to the point. So again, familiarity should not be mistaken for readability or for understandability. Once you get over the initial hurdle, you'll find that it's actually more readable, it's actually more concise to express things using higher order functions rather than express something very trivial that I still find quite interesting. The higher order function map can be used in place of a for each anytime you use a for each. In other words, wherever you are using the for each construct in your code, you can always use the higher order function map instead. Further, I would argue that you not only just can, but you actually should at all times. In other words, you can always use the map construct anytime you come across a for each statement, simply just replace it with a map statement. Or of course a higher order for each rather than the procedural for each. Give it some time, and over time, I think you'll start to see benefits. What is actually a code smell? A code smell is usually said to indicate a potential problem with your software or with your architecture. In other words, it's not said to indicate that there necessarily is a problem with your architecture. It's an indicator that potentially you have a problem with your architecture. So the way I read this, if we contrast it with the word anti-pattern, for example, I would say that anti-pattern rather means that if you do the thing that is an anti-pattern, it's always a problem. It's always a bad thing to do. Whereas a code smell usually is an indicator and not necessarily in itself is a bad thing. So in other words, it's contextual. You need to look at your particular case and then think about whether it actually is a problem or is not a problem. The fact that we have a sort of collective list of code smells is just a way to make it easier for you to discover that you potentially have a problem with your architecture. So code smells, probably a problem, potentially a problem, likely a problem, whereas anti-patterns, always a problem. It's not necessarily that it's definitely end date. And you find these two pieces in your application oftentimes together. In other words, it's not that you are at some point in your application only finding the start date or only finding the end date, but usually you come in contact with both of them at the same time. You have a start date and you have an end date. That would imply that you can probably extract an object that contains both of these two things. So instead of passing around the start date single-handedly, and instead of passing around the end date single-handedly, you pass around the date range. Ben Ornstein also employs this particular example in a great talk called Refactoring from Good to Great. I'm linking that in the description, so be sure to check that out. I think he also explains it very nicely when he says that a good way to identify a data clump is that when one of the pieces do not make sense in isolation, but only make sense together, that's when you know that you have a data clump. So again, think about the date range example. Only a starting date makes no sense unless you have an ending date as well. But of course, again, cold smells are not necessarily always problems. So of course you could have a start date without an ending date. Hypothetically, it could be that the ending date is infinite, for example. But this is purely hypothetical. So data clumps are when more than one object is usually found together, which then implies to you that you could probably extract a new object and put these pieces into the new object. So to make these pieces members of the other object. Another example of a pretty clear-cut scenario could be if you find first name and last name passed around oftentimes together. That would imply that you are probably missing a user object that would encapsulate these two properties. But now we're talking about very obvious scenarios. Let's talk about the scenario that is less obvious. What if you, for example, find a user and a credit card on the same location? Spontaneously, this doesn't feel like a data clump. Even if they're passed around together, it might feel like they're totally different things, and thus shouldn't be coerced into one object, or rather encapsulated and had within a single object. But it entirely depends on your application. If you're in a checkout process, and for example, this is the decided credit card and the decided user, then perhaps it does make sense to pass them around together. If you think about the term payer, for example, then suddenly it makes a lot more sense. It's not a user, it's not a credit card, it's not a user and a credit card, it's a payer for the particular card. And that kind of makes a lot more sense. Just because it doesn't seem like an object spontaneously doesn't necessarily mean that it's not an object. Give it a serious thinker and try to describe the clump using one word. If you can't find a word that does describe the clump pretty well, then you're probably looking at something that wants to be extracted into an object and not kept as separate pieces. Let's just mention what the benefits of this would be. So, for one, the benefit is semantics. So it's easier for a reader of your code to understand what they're dealing with if they have one word. Because they then understand that these two things are two pieces of one thing and not two completely separate pieces. And they have a name for that thing. That's particularly evident in the Ben Ornstein case, where you have starting date and you have ending date. It's suddenly a lot easier to understand what's going on if you're talking about a date range. Lastly, we'll discuss this in more detail some other time, but generally, because of coupling, fewer arguments to a method is better than many arguments. So you are coupling to less things if you have fewer arguments. So coercing pieces of a data clump into a single object reduces the number of parameters that we have in our methods, which from a coupling perspective ought to be a good thing.
Hi, I'm Dr. Dick Costa, the Dean here at Upper Candy College in Fusion.
I've done a previous video talking about why type checking is considered a cold smell. But I just wanted to give you another very quick reason for why that is. When you are type checking, you are switching over concrete types. And when you are switching over concrete types, it means that if you want to introduce another type in your system, and if that type also could occur in a place where you are switching, then that means you need to also switch over that type. I think Sandy Metz puts it quite well when she says that conditionals breed. If you have one conditional, you can be sure that that conditional will cause more conditionals in your code, which is why you should be wary of conditionals. But beyond conditionals, hard coding concrete types in your system makes it difficult or more difficult to change to other types in the future. So the problem is that we don't necessarily know what types we will need in the future. So if you're in a particular place in your code and you switch over types, you have an instance and you switch over the type of that instance, then you need to be absolutely sure about all of the potential possible types that that instance could be of. And of course, because systems usually undergo massive change, then it's reasonable, it's completely sensible to expect that the types of that instance could possibly be different in the future. And I think that kind of sums up the problem of type checking very nicely. When you're type checking, you are coupling to concretions and not to abstractions. And coupling to concretions is less flexible. And in software, we of course want to embrace change. We know that we will often inevitably have to accept change. So we should stay flexible so we have the chance to encompass the change. So type checking is bad because we are coupling to concretions rather than abstractions. So don't ask things what they are, simply send messages to them. Type checking is a code smell. I previously talked about J.B. Rainsberger's argument that integration tests are a scam. In that video, I mainly focused on the combinatorial complexity of integration tests. In other words, the argument that the amount of integration tests you have to write to really have total code coverage are too many. It's a combinatorial problem. There are too many integration tests that you have to write, and thus you shouldn't even try, because it's better to then use unit tests. But I didn't really focus on the scam part that J.B. Rainsberger talks about. So let me emphasize what the scam part is with that argument. So stealing J.B. Rainsberger's example, his example is that if somebody tells you aspirin, but the aspirin gave you a headache, then you would call that a scam. And his argument is that that's actually what integration tests are doing. Integration tests claim to be reducing the number of bugs in your code, but he argues it's more likely that they will increase the number of bugs in your code. Let me explain. He says it's a vicious cycle in this sense. Integration tests allow you to get away with poorly designed systems, with highly coupled systems. Because if you're unit testing, then you really need decoupled systems in order to be able to properly test them, in order to be able to sensibly test them. But integration tests, in other words, allow you to get away with having poorly designed systems, with having highly coupled systems where you can still test them. So integration tests do not give you the feedback you otherwise get about the design of your system. So integration tests lead you down a path of a poorly architectured solution. And a poorly architectured solution probably inclines you to write more tests. Or more specifically, because it's poorly architectured, the cost of writing unit tests is probably very high because it's so coupled. So you choose to not write unit tests and instead keep writing integration tests, and thus further generating the architecture of your application. So in other words, you start with integration tests, you generate the architecture of your application, your application has a degenerated architecture, and because of that, the cost of writing unit tests is too high, so you won't do it, and instead you keep writing integration tests, which further degenerates the architecture of your application, etc., etc., etc. And this is the scam part. It's a vicious cycle that sort of step-by-step degenerates the architecture of your application, and why it still does not actually totally test your system. That's the scam part. Let's talk about CQS, Command Query Separation. Command Query Separation is a term first formulated by Bertrand Meyer. Bertrand Meyer is the creator of the programming language Eiffel, and also the notion of design by contract, which is native in the programming language Eiffel. Command Query Separation essentially states that you should separate your queries from your commands. Kind of intuitive name, right? But what does that actually mean? Let's first get it clear that what we are talking about is methods. In other words, that methods should not mix command operations with query operations. So, command query separation is not a concept that is specific to object-oriented programming. It could be applicable in more paradigms. But what does it actually mean? So, a query is when a method is asking some kind of question. A command that if they are using a method that isn't suffixed with an exclamation point, then they know that they can safely call it without having to worry about whether it will mutate state or not. So to make your code easier to reason about, be sure to separate command methods from query methods. Or in other words, make sure that your methods are not mixing the two things. In other words, make sure that you don't have methods that are both performing command operations and returning results. In other words, acting like a query operation. Make up your mind and stick to it. So this does, of course, sound super sensible. It sounds like a fairly trivial thing to do. But then there are some edge cases. Martin Fowler, the author of refactoring, has famously said on his website that he's willing to break the principle in order to get the pop method, pop on a stack. Because if you pop on a stack, then you are performing a query because you are getting the element, but you're also mutating state because you are changing the contents of the stack. In other words, you are then performing a command. So there are these edge cases, and these edge cases I think beg for another discussion because I would like to make specific videos talking about command query separation in relation to events, in relation to promises, and I'd like to dig into this particular stack example, but we'll do this some other time. So thanks for watching, and as usual, be sure to subscribe if you want more code talks like this. Let me also take the opportunity to say that I've received quite a few subscriptions lately, and I just want to say thank you. It means the world to me. So if you have any ideas or thoughts about topics that you would want to have discussed on this channel, do not hesitate in contacting me any way possible and letting me know that that would be an interesting topic to discuss. Thank you for subscribing. I'll see you in the next one. Let's talk about the concept of sliding in test-driven development. Sliding is also known as fake it till you make it, but here I'll refer to it as sliding. I want to talk about it from three aspects. Firstly, that it helps you to achieve and maintain flow. Secondly, that it helps you increase test coverage. And thirdly, that it potentially helps you reach better production code. Let's take them one by one. But before we do that, let's first define sliding so that we know that we're talking about the same thing. Sliding is when you are in test-driven development, instead of writing an intelligent implementation, you write the simplest implementation possible, which oftentimes means that you return hard-coded values. So you have a unit test that says that a particular method should return, say, the number 2. Then you hard-code the value number 2, even though you may actually know what the correct implementation of the method should be. And then you keep on doing this until it becomes easier to write the actual implementation than to fake a result. Hence the name fake it till you make it. And I guess sliming, the word sliming comes because you sort of input a slimy implementation. You're not inputting the real implementation, you're just sticking some gluey slime in between to make sure that the test passes. Of course, this sounds completely bonkers, and you might say, but why would anybody ever do this? And this is why I want to talk about the 3 reasons. So the first reason is flow, perhaps the most trivial reason also, but that reason essentially has to do with the idea that in the TDD cycle, in other words, the red-green reflector cycle, you want to keep a fast pace. And because of that, people then argue that sliding helps you to achieve that initial momentum and not get stuck thinking about the details of the perfect implementation. But again, I don't really consider this the most important reason. So let's move on to number 2. The second reason is the argument that it supposedly helps you increase test coverage. Remember, test coverage is how much of your code is covered by tests. The reason it increases test coverage is that it forces you to write new test cases. Because you are not allowed to input the actual implementation, or quotation marks, the real implementation, before it becomes easier than sliming the code, then you have to keep writing test cases until you're forced into that position. Which in this case is a really good thing, because that means you get more tests covering more scenarios and hopefully more edge cases of the thing you are testing. And this reason I would argue is compelling enough to argue that when we're doing test-driven development, you should be sliming. To slime is to write the simplest implementation possible and not just write one city use case and then input the real implementation. That does not necessarily give you a lot of security. But as a way of segueing into the third reason, consider the fact that I've been using the terminology I think he's implying that if you do sliming, and if you follow a particular set of rules when sliming, you will incrementally move towards better algorithms. Notice that this is not about writing better tests. It's not about increasing code coverage. It's not about achieving some kind of flow. It's about actually producing better code. So if this is true, I have to say that that's quite profound. So that's it. Those were the 3 points. I hope you now have a better idea of why it could potentially be useful to perform sliming when you're doing test-driven development. Let's recap. 1, it can help you achieve flow in the red-green refactor cycle. 2, it helps you increase code coverage without even thinking about it. And finally, 3, there are those who argue that doing sliming can actually help you reach better production code, which is why I highly recommend you to check out the Bob Martin talk linked in the show notes. So that's it for today. As usual, be sure to hit me up in the comments if you have any questions or angry outrages. And beyond that, be sure to subscribe so that you won't miss the next episode.
These days, there is a lot about this.
Let's quickly talk about the interface segregation principle. The interface segregation principle is one of the solid principles. In other words, it's the I in the solid principles. I find on one hand it's the easiest to understand, but on the other hand, one of the more difficult to understand because it's so easy, so it's confusing. It's like, is that all there is? But it's probably that it's not necessarily obvious what the value is with the principle before you really start to apply it and then actually really see the value. So the interface segregation principle says that it's better to have many small interfaces rather than a few very large interfaces. Or if you restate it just to remember it easily, too many is better than too few. But what do you mean with small interfaces? Let's, as usual, look at an example, and let's take the classic animal example. So assume that we have an animal. Say that we have instance methods for the contents of eating and for, say, moving around, and say, for sleeping, for example. So in other words, we have 3 behaviors that animal can perform, and we call these methods on an instance basis. So we have an instance of an animal, and we call, for example, that instance of the animal. The interface segregation principle is, of course, highly dependent on your particular context and your particular requirements. So, in some sense, we can't apply it now because we don't have requirements. I'm just making up an example on the fly. But stick with me because I think you'll sort of understand what I mean. But again, remember that it's highly dependent upon the requirements. So it's not necessarily so that in 2 systems, small mean the same thing. In 2 different systems, small might mean different things. But back to the example. So the interface segregation principle, in this case, would say that we should not stick the sleep method, the signature of the sleep method, the signature of the eat method, and the signature of the move method into the animal interface. Because we are then constructing a large monolithic animal, when we could in fact instead be creating interfaces for smaller roles, and then give all the necessary roles to an animal instance. So what would an alternative be? An alternative could simply be to take all of these methods and create one interface per method. So in other words, we have a can eat interface, we have a can move interface, and we have a can sleep interface. And in other words, that means that the animal isn't then necessarily an animal, right? It doesn't implement the interface animal, but rather any particular animal implements the interfaces can move, can sleep, and can eat. But what would be the benefit of doing this, you may ask? One benefit, generally speaking, by creating small interfaces, separating out different roles and responsibilities, we are favoring composition over inheritance, and we are favoring decoupling over coupling. If you think about microservices, it's much the same thing. Instead of creating one giant monolithic app, we are creating a bunch of small responsibilities and then composing them together in the way that we want to use them. But let's talk about something more hands-on. Now, it's kind of silly because in the example I chose, probably all the animals we can possibly conceive of will be able to, in some form or another, move and eat and sleep. Probably. I mean, metabolism, right? But say that we are building some kind of animal simulator, or we are building some kind of game, right? With this design that we currently have, with all of the small interfaces, if we would want to have other species, such as plants, for example, say trees, then those couldn't necessarily move. And previously they had to be in a different inheritance hierarchy than the animals. But if we separated the small interfaces, so that if you remember we have can move and can eat and can sleep, maybe it would be reasonable to say that trees, that some species can, for example, eat, but they can't sleep or they can't move. So trees can't move, trees can't sleep, but trees do have some kind of metabolism. They too consume energy and produce waste. So it might seem contrived, but the point I want to make is when we are favoring composition, when we have small roles that objects can play, it's much easier to design new objects without having to make entirely new classes. So that's it. That's most of the stuff you need to know in order to get started with the interface segregation principle. Again, remember, it's better to have many small interfaces than a few very large ones. Or stated super simply, too many is better than too few. So thanks for watching, and as usual, if you have any questions or comments or any outrages, do hit them up in the comments. And apart from that, if you want more code videos like this, be sure to subscribe. Let's talk about Iterator Pattern, the design pattern, Iterator. If you come across design patterns, you've likely come across the Iterator Pattern. The Iterator Pattern is a way of separating the algorithm from the container. And in this case, the algorithm could refer to, for example, a search algorithm, and the container could be a list, or an array, or a linked list, etc. To be honest, I feel this sounds kind of sort of esoteric and difficult to understand why it would be useful. So let's talk about a more, let's say, simple example. I came across this example some years ago, and honestly I can't remember whether it was actually directly in relation to the Iterator pattern. And honestly I can't either remember where it is actually from. So if you recognize this example, please do show a link in the comments, and I apologize to the authors for not referring. But consider the following. Say that we're building some kind of banking system, and that in our banking system we have an account class. So it's an oversimplified example, but assume that we in this account class have a section that contains deposits. Again, it's oversimplified because in a real-world scenario you would of course probably use some kind of object to represent a deposit, but in this case we're just going to use a primitive. So say that deposits are represented by numbers, in other words, the amount actually deposited. Okay, further assume that we then want to use this account in the following way. From the outside, for some reason, we want to be able to iterate over all of the deposits, and then, as relevant to this example, could do something with it, say, print. But the key point is that we want to do something which is non-mutating. We simply want to use these deposits, but we don't want to change the deposits within the account. So in order to get access to these deposits from the outside, we need to somehow expose the list out of the account. And this is the happy moment when we realize that in languages such as C# we have members that can be publicly gettable but privately settable. So it feels like a perfect such scenario, so we would simply then mark the list to have a public getter and a private setter. Fine and dandy, we call it a day, and as the story goes, this is of course super hypothetical, while we go that won't just change the user's copy, that will actually change the array within the account. So it's a classic case of the problem of mutability. While you are thinking that you are only mutating your copy, you are actually changing the content of the account, or you are changing the contents of the list of deposits within the account instance. So let's get back to the iterator pattern. How could the iterator pattern help in this case? Well, the iterator pattern hides the underlying collection from whoever is using the collection, which is exactly the scenario. So if instead of in our account class we would make the list of deposits publicly gettable, we could simply implement some kind of iterator pattern, which in C# or .NET would be the enumerable interface. This would mean that from the outside, instead of grabbing out the collection and then using that collection in, for example, a for each, we could now simply iterate over the actual account. We simply pass the account to the for each, and then in each iteration, you will have access to one of the primitives representing one of the deposits. Alright, let's wrap this up. There are many more ways of using the iterator pattern, and this is just one. But I think it's important to understand that some of the sort of school book examples that you get when you're learning iterator pattern is not necessarily at all of the cases for the iterator pattern. Again, it might feel as an esoteric pattern that you would hardly ever use, but it's actually highly usable and highly useful in some scenarios. Alright, that is it. If you have any questions, comments, or angry outrages, as usual, do hit them up in the comments. And if you want more cool talk like this, be sure to subscribe. The best code comments are the unwritten code comments. What do I mean? Today we're going to tackle the following question. Should I write comments in my code? The way school drills us is sort of to answer yes to this question because we're pumping in assignments with comments in every assignment. Unfortunately, I would say that the answer generally to this question is no. You should not write code comments. You should not write comments in your code. The reason is actually very simple. If you're writing comments in your code, that means that your code is difficult to understand without the comments. If you haven't seen my other video on making code read like pros, be sure to check out that video. But essentially that's the point. The problem is not that the problem we're facing requires code that is inherently difficult to understand. The problem is that you created a very strange solution, that you've chosen a poor abstraction, that you built a difficult to understand solution to a problem that could be easy to understand. Now it's entirely possible that your case is different. But consider this interesting statistic, for example. The average driver thinks he or she is a better driver than the average driver, which of course is sort of logical impossibility. So I think we perhaps use the argument that our case is different in sort of the same manner. So we sort of spontaneously say that our case is different when in fact it's kind of just like any other case. Those of us who've been programming in school, again, we've sort of been taught, most of us, to hand in assignments with code comments. My take on this is that I think that this stems from the need to assess that students are understanding semantically what they're doing and not just tactically. But of course that's a kind of strange thing to bring to the working environment. In the working environment we of course assume that our colleagues semantically understand the code that they are writing themselves. It's a question of making them semantically understand the code that they didn't write themselves. And again, the solution to this is not code comments. It's to write better code so that when they read the code, they can actually understand the code. So it seems to me that we're sort of slowly getting rid of this obsessive relation to code comments in the school environment. But it's of course super important that when we're eliminating code comments from academia, that we're actually replacing it with something else and not just removing it. Because inevitably, I mean, we've all been beginners at writing code, and if you think about the code you wrote very early on, you'll realize it's, let's say, not very nice. And code comments at least then help other people understand what you were trying to do. And in the case somebody was marking your assignment, they would understand what you meant and why you did and all this stuff. So it's very important that when we are removing code comments, it's not that we are not replacing it with anything. Because noobs may still continue to write code like this. In the school environment, I would architecture. Going back to why we don't need code. Another good reason is testing. In dynamic languages, it's sometimes really hard to understand, for example, what the method can handle getting because of duck typing. You have a method and it takes an argument, but because you don't know the type of the argument, it's very difficult to figure out what are appropriate arguments and what are not appropriate arguments. And this is, of course, one scenario where people could use code comments. But this is a scenario where testing might actually become super useful. So your tests exercise your code, and in your tests, you can then look into and understand what is okay to pass as an argument and what is not okay to pass as an argument. So the relationship between testing and code comments, and in other words, testing and documentation, is a whole discussion in and of itself. And as usual, we're only scratching the very surface of it. So we'll dig into that specific discussion another time. But just be aware that a lot of people, including myself, argue that different levels of testing replace code comments because testing can be used as documentation for your system. Now, there's a lot of talk about why we shouldn't use code comments. Is there any time when it is actually appropriate to use code comments? Generally, I can only think of one scenario where I'm totally fine having code comments. That is, if you have an algorithm where performance is very important. The reason I say that performance has to be important is that because abstraction usually crushes performance. So if you want to maintain performance, you usually want to not abstract your code. And in other words, you may end up with an algorithm that's a bunch of lines long. So usually the argument is that if you have something that you would want to call an algorithm and it's more than a few lines, and you would use that as an argument to say that, well, I need code comments because I need to be able to annotate this algorithm, then I would say that, okay, if you're expecting the algorithm to change, then you should still break it up into multiple pieces. Even though you feel that it's an algorithm, you should still break it up into multiple pieces because of the fact that you are expecting change. Because you are expecting change, it might have to change in the future, which means that people will have to understand it, which means that abstraction is the right tool for you. If it doesn't have to change, if you're not expecting change, then honestly, I would ask myself whether you actually need to annotate it or not. Do you actually need code comments in the algorithm if you're not expecting the algorithm to change? I mean, why do you then have the comments? Instead, wrap the whole algorithm in a method that has a sensible name. And if it has a sensible name, you don't need code comments because the name is self-explanatory in how to use it. We go back to the scenario where you were expecting change. If you then argue that performance is important, then I say, okay, yup, code comments. If performance of a particular piece of algorithm is important, then yes, use code comments to make the algorithm understandable because you can't use abstraction. But beware of premature optimization. When we're arguing that we need to increase performance, it should be because we have done testing and we have come to the conclusion that we need better performance than we currently have. Do not optimize just because you think you will need to optimize. Do it when you know that you need to optimize. And of course, as usual, we're envisioning a perfect world, but in reality, a few other edge cases sort of hit us, and in some of these, I would say, yeah, it's okay to have a temporary code comment, and then we'll get back to removing that code comment in the future. But generally, the way I stand now, I think the only reasonable reason is if you need to maintain performance and have some kind of algorithm that grows complex. In all other scenarios, you don't need code comments. Okay, so that's it. I'll stop ranting. Key takeaway, the best code comments are the unwritten code comments. Should I write comments in my code? No. Rewrite your code, refactor your code to make it self-explanatory. Make sure that people understand your code without having to read comments. That's it. If you have any questions or comments or any outrages, hit them in the comments. As usual, thanks for watching. I hope to see you next time. Be sure to subscribe so that you won't miss it. Here is a cool one. Validation versus verification. Both of these deal with the correctness of the software. And in the most easiest terms, they answer different questions. Validation answers one question, verification reads a sequence of numbers as input and produces a sequence of numbers as output. What the program is supposed to do is essentially that it's supposed to sort these numbers. So, assuming that what we want is that we want numeric sorting in ascending order. If you would give the program, say, 2, 3, 1 in that order, and it produces 1, 2, 3, then that means that the program is working. Importantly, it means that it's working from a verification point of view, but also from a validation point of view. Let's talk about why that is. So, it works from a validation point of view because we said that what the program is supposed to do is that it's supposed to sort in ascending order. Validation deals with whether we have understood the requirement correctly. So the requirement was ascending sorting, and we interpreted that correctly because we interpreted to mean that if you have 3 to 1, that means that you should produce 1 to 3. That's the validation point of view, or the validation part. The verification part says that, okay, assuming that that's our understanding of what the software is supposed to do, what are the actual results that we get? So assume that that was our understanding. So you can think of it sort of as a two-step process, right? Your friend comes to you and says that, okay, what we need is that we need a program that sorts numbers ascending. And you say, okay, so that means that if I get 3 to 1, then I'm supposed to produce 1 to 3. If I get 3, 3, 1, I'm supposed to produce 1, 3, 3, etc., right? And now we're sort of using these cases to understand the scenario, but you could, of course, use a number of other ways of understanding your scenario and reaching an agreement with your client. But assuming that you reach some sort of consensus, you say, your client says, yeah, that's actually the thing I'm talking about, that's the software I want to have built, right? Then you achieve validation. But when you're then writing up this program, if you would write up the program such that it doesn't actually produce these numbers, then you've understood the requirements correctly, but you failed to implement the software according to the requirements. In other words, that means that validation is about interpreting the requirements correctly, whereas verification is about actually operationalizing these requirements correctly. But then you might ask yourself the question, okay, but why would anybody ever care about sort of defining up this erroneous piece of software to reason about what kind of error we are facing? Well, put yourself in this scenario. Put yourself in a, I guess, all too often happening scenario that somebody says to you that, oh, the software doesn't work, or this page doesn't work, or this thing doesn't work, right? Step one. What is it that actually doesn't work, and what do you mean with doesn't work? Right? Validation and verification is one attempt at sort of bringing some level of sanity into that discussion. So, in other words, whenever you are faced with one of these scenarios where you have to figure out what somebody means when they say that it doesn't work, you can approach it with the concepts of validation and verification. So you say, okay, do you mean that we misinterpreted what you want the system to do? Or do you mean that we successfully understood each other in terms of what the software is supposed to do, but that's not actually what the software does? This is not just an issue for us as software developers when we are in discussion with our clients. Let's be honest, this is actually an issue with ourselves when we're debugging our own code, right? I think you can all relate to the situation where you're sort of, after hours and hours of trying to figure out where the problem lies, sort of feel like you want to bash your head into the keyboard. Oftentimes, this situation, I would argue, arises because we're sort of narrowing our focus and forgetting what we're actually intending to do. And when we forget what we're actually wanting to do, we're sort of jumping back and forth between validation and verification thinking. Also, as a side note, this is kind of what driven development is a lot about zoning in on, or even more specifically behavior-driven development. But that's a whole other discussion. So validation and verification can then be used as a tool to understand in what sense your program doesn't work. Is it not working from a verification point of view, or is it not working from a validation point of view? Quick recap. A validation error is that you misunderstood your requirements or misinterpreted your requirements. A verification error, on the other hand, is when you've understood your requirements correctly, but you've failed to implement what you've understood correctly. Of course, it should be said that when I then explain verification errors in that sense, I'm then assuming that you have interpreted the validation part correctly, that you've interpreted the requirements correctly. I mean, it's of course entirely possible to have an error which is both a validation error and a verification error. I mean, it's of course possible to outrageous. And apart from that, be sure to subscribe so you won't miss the next episode. Thanks for watching. It probably makes a lot of sense. It's actually kind of... Hello?
Integrated tests are a scam. That's the title of a great talk by J.D. Raynsberg. The talk has also been referenced in a number of other talks, one by Gary Bernard and one by a guy, unfortunately I can't remember his name right now, but I'll link all of these three talks in the description, and I highly recommend you to actually check out all of these talks because they're excellent if you're into testing and if you've been thinking all about unit testing versus integration testing. The claim in the talk, as far as I understand it, is that we should not be doing integration tests at all. J.D. Raynsberg gives a potential solution or an argument as to what we should be doing instead. I won't dig into that now, but I want to just spend a few minutes emphasizing what the problem is that he outlines. The problem can sort of be summed up in a single word. The single word is complexity. Integration tests have too much complexity in combinatorial terms, in the sense that there are too many tests to write if you're doing integration tests, so you should not trust yourself with the task of writing and maintaining all of these tests. So again, the point is combinatorics. If you're doing unit testing, you're isolating, right? So when you're doing unit testing, you're testing a single unit and you're mocking all of the boundaries, which means that the only cases you have to test are the cases of the components under testing. So let's be very specific. Let's say that we have a fish class, and the fish has a method which is called eat. And the fish is faithful to have two states, either hungry or it's not hungry. If it's hungry and we call eat, then the fish is fed. If it's not hungry and we call eat, then nothing simply happens. That means we have two states. We need to test eat when the fish is not hungry, and we need to test eat when the fish is hungry. The problem is that if we have this fish and we put this fish into a context, when we're integrating with the fish from some other place, then we have to test these two states for every other state that we want to test. It sounds super confusing. Let me be more specific. So say that we also have a pond class, and all of these fish live in the pond class. So essentially, pond is a glorified collection. The pond has a bunch of fish, and say that the pond instead has a feed method, and the feed method takes maybe a number of representing the amount of food. And what we're interested in, for example, I'm just making a hypothetical system, what we would be interested in would be, for example, how much of the food actually went to feeding the fish and how much went to waste. In other words, how much of the food wasn't eaten because no fish were hungry. So this means that when we're testing the feed method of the pond class, we need to test it with fish of different kinds. We need to test it with hungry fish and we need to test it with non-hungry fish. So in that case, we need to instantiate a bunch of fish, some that are hungry and some that are not hungry, and then test the feed method of the pond class with fish of different kinds. Now, this doesn't sound too bad, but if we scale this up, theoretically, it's actually quite absurd. Because what we actually would want to test in the pond class is the fact that the pond class delegates eating to each fish. What the responsibility of the feed method actually is iterate on the collection of fish and then feeding all the fish. It shouldn't necessarily care about whether they are hungry or not. So imagine, for example, that we not only have a pond class, but imagine also that we have, say, a garden class. So a garden, again, a glorified collection. So a garden is a collection of ponds, and a pond is a collection of fish. Now, say that we there also have a feed method, right? Maybe it makes more sense to think of it in terms of a maintenance method or something like a maintain method. So it would be more generic. So we would say maintain, and then there would be lots of garden stuff going on, such as watering the plants and feeding the fish and whatnot, right? But for now, just to keep things simple, think of it in terms of that the garden also has a feed method, which essentially calls feed on all of the specific ponds. And remember, again, the thing that we're interested in this system is that from the utmost class, from the garden sense, we want to know how much of the food actually went to feeding the fish and how much went to waste. So let's just feed, the garden plants called feed in all of the ponds, or the ponds called feed in all of the fish. Some fish are hungry and some fish are not hungry. A hungry fish consumes a single unit of food, and then in the end we get back a number that represents the number of fish that were actually not fed. Or in other words, the number representing the amount of food that were not consumed. Okay, how do we test the garden plants? The number of states when we're testing the garden, the number of states depends on the number of states that we have in the pond. And the number of states we have in the pond depends on the number of states we have in fish. And again, if you then return back to unit tests, what unit tests have to do is simply to test that the garden delegates appropriately to the pond, and that the pond delegates appropriately to the fish. So the number of tests we have to write when we have isolated unit tests are significantly fewer. So if you send this up, you'll realize how quickly this becomes absolutely absurd. Let's generalize. The thing is this: if instead of talking about a garden and a pond and fish, let's talk about A, B, and C. So it's actually a combinatorial problem. So the number of cases we have to test in A is the number of different cases we have to test in A times the number of different cases we have to test in B times the number of different cases we have to test in C. A lot. Going further, if we're also integration testing B, then the number of cases we have to test in B are the number of different cases in B times the number of different cases in C. And then if we're unit testing, we would also be testing the number of different cases in C. So again, really quite absurd. I'm not saying it's easy, because only doing unit testing means that you're probably not testing whether you are integrating the components correctly together, which is why people usually do integration testing. So you won't dig into the answer of how to actually do that now, but I highly recommend that you watch through J.B. Rainsberger's video, where he does give an answer to how to write more unit tests that ensure that your units are not only functional when in isolation, but actually are coupled in a correct manner. So that's it for today. If you find it more confusing than helpful, please let me know in the comments so we can dig down further. And if you appreciate this video, please give me a thumbs up. It helps massively. And for more content like this, of course, subscribe. Let's talk about Liskow's substitution principle. Liskow's substitution principle can be held in the solid principles, in the solid object-oriented design principles. I find Liskow's substitution principle to be sort of self-fulfilling prophecy, where people tell each other that it's the most difficult principle to understand, and through that, making it the most difficult principle to understand because nobody actually takes the time to understand the principle. And in fact, the principle is actually really, really simple. So the principle states that if you have a base type and you have a subtype, in other words, if you have a base class and you have a class inheriting from that base class, then the subclass should be substitutable for the base class at any point in the program. In other words, in every place where you're using the base type, you should be able to swap that instance for an instance of the subtype without causing any unwanted behavior in the program. And that's it, right? It's not any more strange than that. It just means that you have an inheritance hierarchy, and as soon as you're inheriting from the base class in a way that makes the subclass not substitutable for this particular base class, then you're breaking the Liskov substitution principle. That's simple. To really dig into the details, I find it most helpful to think about preconditions, postconditions, and invariants. If you're not familiar with conditions, postconditions, and invariants, don't worry, I'll make another video and I'll link that in the description as soon as it's done. But very simply, preconditions are sort of the entry conditions for a method. To be able to call that particular method, whatever is stated in the preconditions must be true. Postconditions are sort of the other end of that spectrum. Postconditions state whatever must be true when the method has been called. And invariants state what has to be true at all times in the program. So in terms of Liskow's substitution principle, here's how this helps us. Preconditions in the subtype must be the same or weaker. I'll get into what this means now. Postconditions subtyping, right? We're talking about something being a subtype of something else. So cats are a subset of all animals, right? Boxes are not a subset of all animals. And so to understand the whole preconditions, post-conditions, invariance thing in this substitution principle, it helps to think about the robustness principle. So the robustness principle says that you should be liberal in what you accept from others, but conservative in what you send. So in other words, that means a method should be accepting when users of the method are sending in incorrect values, but it should be very helpful with itself sending incorrect values. I think the history of this is saying it's from networking or something like this. It's actually a very good principle, and there's this joke that if this were applied to people and not only to programming, the world would be fantastic. Just saying. I'm not at all religious, but it's not like a goal, right? So the robustness principle essentially says the same thing as it demands in terms of preconditions and postconditions related to the substitution principle, right? So the subclass, a method in the subclass, must receive everything that the base class is expecting it to be able to receive, right? The whole set of possible values. But because it's liberal, right, it may also accept a bit more. So it's a set of all the possible values that it may receive given the type of the subclass of the base class. But it's a larger set, so it may also receive some more. The post-condition of the subclass, however, must be the same or stronger, right? And stronger means that it's a subset, right? So methods in the subclass must either return values from the same set, right? Or from the same domain. Values from the same set. In other words, the same types of values that you get from the base class. Or, if it doesn't do that, it must return a subset of the set of possible values, right? So, in other words, you would never see anything unexpected from the subclass, right? You would never, because you're conservative in what you send, right? So you would send either anything that the base class sends, or you would send something even more restrictive, right? It's all about being able to depend on the subclass following the contract to have no surprises. And invariance, lastly, again, invariance in the base class must be followed or must be stronger in the subclass. In other words, thinking about sets again, the set of possible states of the subclass must either be the same as the set of the base class, or it must be stricter. It must be a subset of the set of states of the base class. I know this gets super confusing with all the sets, but if you really start to think about it, it's not actually that strange. So yeah, actually, I wouldn't argue that this substitution principle is difficult to understand. You just really have to think about it. What's difficult about the list of substitution principle, I find, is to actually follow it. Because when you really start to understand it, you understand it, but most of the time you actually do even know that we're subclassing too much. Saying that the list of substitution principle is bad because it's difficult to follow. It's kind of like doing testing for your system being difficult to test. Testing a system that's difficult to test is an indicator that your system is poorly architected, that it's highly calculated. Similarly, violations of the list of substitution principle is an indicator that your system may be poorly architectured in terms of inheritance. You may be overusing inheritance in places where inheritance should actually be. That's it for today. For more stuff like this, be sure to subscribe.
You've probably heard that type checking is considered a code snap. In other words, type checking is something that you should avoid in your program. And when I say type checking, I mean switching over what type something is. In other words, asking an object what type it is of, and then making a decision that's different depending on what type the object actually is of. Let's talk about why that is. So the answer depends on whether you're in a statically typed language or a dynamically typed language. Let's first cover dynamically typed languages because the answer is really simple. In dynamically typed languages, you should simply not be type checking because in dynamically typed languages, you should use duck typing. If you're not familiar with duck typing, I've got a whole other video on duck typing, so check that out. Now, let's talk about statically typed languages. You should not be performing type checking because if you're performing type checking, that means that you at some point lost track
What do I mean? It means that you, at some point, actually know the type of the object, but you've abstracted in a strange way, which means that you've now lost track of the type of the object. Looking at it from a different perspective, consider this. Every cat is an animal, but not every animal is a cat. So in other words, what happens is that you are asking an animal whether it is a cat, which of course is understandable, because if you want to treat it as a cat, you don't want to treat it as a cat in case it's a dog, or something totally different. But the point is that you at some point did actually know that it's a cat, and you've lost track of that, and so now you only know that it's an animal. To really drill that point in, think about static typing. If you're switching over the type of something, you're not actually asking what type it is of. You are asking what subtype it is of. Because the fact that you have that object in that particular place in the program anyway, means you have some type information about the object. In other words, you can't just accept anything unless, of course, you're accepting super general types in your program, such as object, but then you're not really using the concept of static typing to your advantage anyway, and that's a whole other discussion. But in other words, in your method, you've accepted a base type, and now you're switching over which subtype of the base type this particular instance is of. So, that means that you did, in fact, because it hasn't been instantiated, you did, in fact, at some point in your program know what particular subtype this thing was of, but you've lost track of it. Okay, now let's stop ranting now. I currently really believe that there are no cases where you actually need to switch over types. Again, because if you are switching over types, that just means that you've architectured your solution incorrectly. It doesn't mean that the problem necessarily needs you to switch over types. If you have an example of some particularly true scenario, please do feel free to outline that in the comments, and let's discuss that. But that's it for today. Be sure to smash the like button if you like the video. If not, please let me know in the comments. And if you want more stuff like this, be sure to subscribe. Right.
Hi, I'm Dr. Dave Costa, the Dean here at Robert Kennedy College in Zurich, Switzerland.
Object-oriented design patterns. Why do we actually need them? The usual explanation is that depending on the problem that you are facing, sometimes may prove more or less suitable for a particular problem. So the argument being, for example, if you need to dynamically construct objects, then factory pattern is suitable. If you need to, at runtime, alter a particular algorithm, then strategy pattern is useful. But I recently come across a different explanation that I find is much more interesting in regards to why we actually need design patterns. Or let's say, why design patterns is even a thing. So think of it this way. To talk about why we need design patterns, you need to ask yourself the question, which language am I actually working in? So we're going to simplify the world and only talk about two dimensions of languages. We're going to talk about functional languages and object-oriented languages. But also we're going to talk about whether they are statically typed or dynamically typed. So in other words, that puts us in a situation where we have four different kinds of languages. In other words, we have object-oriented dynamically typed languages, we have object-oriented statically typed languages, we have functional dynamically typed languages, and functional statically typed languages. Easy, right? So simplifying it too much, we can think of it this way. Dynamically typed languages are more flexible, while statically typed languages are more safe. In other words, I mean they are type safe. So static checking is able to find errors much more easily in statically typed languages. Whereas in dynamically typed languages, you actually have to run the program in order to see whether you have what would be in a static language a compilation error. So if we look at all these four categories of languages, most design patterns exist because statically typed object-oriented languages need them in order to achieve the same flexibility, runtime flexibility, that all of the other languages have for free. Remember, disclaimer, I'm not saying that this is the only reason we have patterns. very great reason for the existence of these patterns. So let's recap to really nail this in. So, statically typed object-oriented languages need patterns to achieve the same flexibility that functional languages and dynamically object-oriented languages have for free. If this seems confusing, let's talk about an example. Probably the easiest example is strategy pattern. It's probably also one of the easiest patterns. Strategy pattern essentially is that you want to vary an algorithm at runtime. So I guess a canonical example is sorting, right? You may want to sort using different algorithms, and you don't want to at compiling time couple yourself to a particular sorting algorithm, so you can instead at runtime choose your sorting algorithm. If you think about this, if you have a statically typed object-oriented language, and you have a method called sort, how would you inject an algorithm to the method sort? The short answer, of course it's multifaceted again, but the short answer is you can't. But with strategy pattern, you can. So what we do is that we create a simple interface, say I sorting algorithm that only has, say, one method called compare or called sort or something like this, and then we pass anything that is an I sorting algorithm. Which means that we've essentially created an interface that wraps one method, right? And we've created a contract for having a single method with a particular signature. If you think about the other end of the spectrum, a functional language, of course, that's for free in a functional language, because in functional languages, you have higher order functions. And a strategy, in this case, an algorithm, is a function. So you have a function called sort. And to the function sort, you pass your particular sorting algorithm. So that's for free to build into the language. And if you look at statically typed functional languages, then if I oversimplify, then the function signature is a type. And in that case, the sorting algorithm simply needs to have a certain type. But as long as it's a function that corresponds to that type, then we can pass in any sorting function of our wishes. So again, it's for free in both kinds of functional languages. In dynamically typed object-oriented languages, it's also for free. But the point is again that we are then losing static type. Let's do the whole same discussion for factory pattern. So factory pattern exists because we want to be able to at runtime change the type of an object we're instantiating. In other words, depending on different scenarios, instantiate objects of different kinds. For example, it might also be that we want to instantiate using some kind of complex logic or passing in a complex series of arguments or something like this. But essentially that we at runtime want to vary object instantiation. If we only look at a scenario where we want to vary type, right? Say that you have cats and you have dogs, and then you have an animal factory, and the animal factory instantiates your cats or dogs depending on some scenario. Now, in a dynamically typed object-oriented language, we don't, to the same extent, we don't really need a factory because classes are objects, and objects you can pass around. So in other words, instantiation, if you think about Ruby, for example, you can pass the class as an instance and then call the new method on that instance. In other words, instantiating an instance of the class. So again, that means factory pattern comes for free in a dynamically typed language. But again, the point is that we've lost the type safety. So to have that kind of behavior in a statically typed language, we need factory pattern. And then we have dynamic object creation, but still maintain type safety. And again, in functional languages, that's sort of for free. I'm saying sort of because there's no super obvious translation to functional languages because we oftentimes don't have classes in the same sense. So the analogy is kind of difficult to pass over. But again, higher order functions. So you can have a function that takes a function and returns a function. You can, in other words, you can get a function back from a function. I guess I would somewhat the equivalent of factory returning an instance of a class dynamically. So to me, this seems to really be the reason why we have patterns. be wary when people are trying to bring the classical object-oriented design patterns into dynamically typed languages, because it's not always obvious that they have an application. Again, we have to ask ourselves, is it because it somehow helps structuring the code to make it more, say, phonetically readable or understandable, to essentially help with cohesion? Or is it because we're trying to solve something that we think is unsolvable otherwise? Because it seems to me that most of these problems are actually completely solvable for free, quotation for free, or rather quite naturally, in dynamically typed object-oriented languages. Okay, then, quick recap. We've been talking about functional languages, object-oriented languages. Both of these can either be statically typed or dynamically typed. And in regards to classical object-oriented design patterns, most of the time you don't need them at all in functional languages because for free. And most of the time you don't need them at all in dynamically typed languages. But in statically typed object-oriented languages, we need them to achieve the same kind of stability that we have in these other languages. But the question is, of course, type safety. So it seems to me that probably people have introduced design patterns in order to be able to stay in the statically typed world while still gaining the benefits of dynamic typing. So that's it for today. I have a whole other interesting discussion around Iterator Pattern, but let's discuss that in another video. So be sure to subscribe so you don't miss it. Now, today we're going to talk about the principle tell, don't ask. The design principle tell, don't ask. Tell, don't ask is a design principle whose intent is to reduce control coupling. Now, what is control coupling? Control coupling is when one object is very concerned about controlling the control flow of another object. In other words, when one object is really concerned about telling another object when it's supposed to do things, when in fact that object itself could itself control when it should or should not do particular things. It's actually a very simple design principle that can have immensely positive consequences for the design of your code. So this principle is probably most easily understood by considering an example. So consider this. Assume that you have a class called fish. And the fish can do two things. It can eat, and you can also ask whether it is hungry. So the fish class has two instance methods. One is hungry, which returns a food, and the other method is eat, which is a mutating method that essentially causes the fish to eat. So assume then that the user of fish, say the program that has, or the ocean or whatever, that has an instance of fish. Let's say that that program first calls is hungry and uses that in an if statement to switch over whether the fish is hungry or not. And then depending on the answer, decides whether to feed the fish or not to feed the fish. This is essentially control coupling. The outside, i.e. the user of the fish, is very concerned about the internal state of the fish and uses that information to determine whether or not the fish should be fed. But tell, don't ask says that actually this is reversed. The thing is that the fish knows whether it should be fed or not. So that state should not necessarily leak to the